So I'm here to talk about some tools to interpret gravitational wave observations. This is a ridiculously huge field. I'm going to demonstrate some cases that many of the things that we've talked about and challenges that we have can be cast in terms of one of these two things. So to keep the scope of this talk finite, I'm going to talk about two specific implementations of how you can go about interpreting individual sources and populations of them. So we can talk about translating some of the science goals that have been demonstrated previously, and that I'll also add some additional ones, can be translated into astrophysical results. During this talk, and particularly in the middle, I'll try also to connect to the themes of today and yesterday in terms of some of the techniques that you can use to make these tools viable for larger scale astrophysical analyses. Use of emulators, hardware optimization, large-scale workflows, the cyber infrastructure that makes all of this possible. And I'll conclude in my ridiculous number of slides with some of the interesting applications that I think this audience will care about. Fortunately, people have already covered a lot of this, so I can skip over this quickly. How many observations are there? What is the size of the big data that we have to work with? Fortunately, it's not ridiculously big. There's only a couple that have been published so far. And as was mentioned earlier today, there are public alerts which suggest that there will probably be plenty more coming out of O3 of order, let's say, 1 a week for BBHs and 1 a month for BNS alerts scaled so far. At design sensitivity, we're talking tens of binary neutron stars and thousands of binary black holes per year. So that's a lot of data. And you can make it even larger by trying to go in deeper into your search and look for subthreshold events, another factor of order of 100, depending on what you want to do. But for the immediate future, we're not talking about the millions of events per year that you're going to get with third generation instruments, which, oh my God, that would be horrible. Fortunately, we're only going to have to deal with a few thousand binary black hole events per year. I don't know what I'm going to do, but we'll figure it out. No, I do know what I'm going to do. So the data size is actually surprisingly modest compared to some of the things that we heard about from high energy particle physics. So the tools that we have to do this, or which are common for, which is why I'm talking about both parameter estimation and population inference, are surprisingly common and standard statistical tools. They're not the same, they're not the really ridiculously large big data, blind, non-parametric stuff that some of the things that you may have heard about yesterday. For parameter inference, I mean interpreting one individual source. This is something that Sean covered earlier in his talk. The idea is that we're trying to predict from our observations, but recover the masses, let's say, and some spins and some properties of the sources that we see. These are 90% credible interval posterior distributions, and we do this, as Sean said, by doing a simulation. Here's my dance. You're emitting gravitational waves. You go in together. You come together and merge and ring down. That's my patented dance. You predict the gravitational wave strain. You compare it to observations many, many, many times. You do your happy MCMC. You get a posterior distribution, and that tells you what it is that you saw. Then the idea with population inference is you take what you just got and do it again, trying to figure out what is the population of sources responsible. So to do this, you take in all these individual events, and then you say, how sensitive is my network? Well, these networks are more sensitive to things that are bigger, because bigger things emit more gravitational waves. So the absence of sources up here is striking. Also, we don't really lose sensitivity. Gravitational networks don't lose sensitivity as you go this direction mass ratio. So the absence here is pretty striking. Down here, yeah, okay, it's harder to see really tiny things. So the absence here and here, even just by eye, can tell you that when you start to stitch things together, that you'll have interesting things to say about the mass distribution of sources that you have. So this is the LIGO result for the mass distribution of the larger black hole. And you can see just pretty much by eye, by looking at this plot, big black holes you don't find. And you can either get big by going this way or this way, and you don't have anything basically over here. Now, as I said, pretty much all these science applications that we're interested in, Hubble constant measurements, nuclear equations of state, modified GR, all fall into this same framework, which is convenient but annoying when you have to give a talk in 15 minutes. Fortunately, all the frameworks are standard. You have basically a likelihood that you create in the usual way. This is an inhomogeneous Poisson likelihood. And then you use Bayes' theorem, and then you turn your favorite crank. The problem, of course, is even with only a few thousand events, turning your favorite crank can actually get surprisingly annoying. And particularly when your models, your gravitational wave signals, take weeks to run, that would be a problem. But even if they take only seconds to run, that can be a problem, which leads us to consider using surrogates and efficient approximations. But then you have approximations which introduce systematics on top of the approximations that you're probably making in order to get to create those models in the first place. So model cost is extremely annoying, and this will be even more annoying when we talk about astrophysical populations. The second problem is, okay, great, you can do it, but we just talked about low latency alerts, and a lot of you are astronomers who point telescopes. So you probably want these sensors as fast as ridiculous as possible, often on ridiculous speeds, sometimes even before we actually have sent out an alert at all, some pre-warning. The efficiency needed to achieve that type of goal is very, very high. And of course, the classic challenge is understanding real data. Well, real data is not pure Gaussian noise, which is what I'm going to focus on in this talk. But that is hard. All right, so Sean already went through the basic idea of parameter inference, and I'm going to use that to motivate some of the design choices in the algorithm that I'll talk about next. We're applying Bayes' theorem to a signal in Gaussian noise. So here's a Gaussian, expressed in terms of inner products, signal minus data squared. Now, this involves an inner product, so this is a long time series, and this is our gravitational wave strain, what Deirdre was talking about in her talk. Now, the problem with this is it involves two horrible, messy things. Not that horrible, but still horrible. One, you have to solve GR. Okay, that's bad. Okay, we heard about how bad that was. But let's suppose that we have someone who's got a really clever approximation, and they spent months and months tuning it. It only takes them an hour, okay, maybe a minute, no, a sec, no, a fraction of a second to run. Even then, well, you've got some problem if you have to do this millions and millions and millions of times to do an MCMC. So the likelihood cost is very high. And even if you made that 0 and you were evaluating this basically instantaneously as a frequency domain model, even then you still have to manipulate a long sequence of a long array, and this cost of just evaluating it, even if you have effectively no cost besides populating the array because you have an analytic formula, even then the evaluation cost can still be too high because you're hauling around doing this in a product. So the key things that one does to make these, some of the key things that one does at a high level to make these codes faster is make this cheap. So how do you make it cheap? One, you make H cheap. So how do you make H cheap? Well, one is you look up simulations like numerical relativity. Then you have an answer. You don't have to do any simulations. You're just looking it up. That's great. And it's also fantastic because then you're not emulating anything. You've got the real answer. The problem is NR doesn't go everywhere. It does go a lot of places. And then you're left with another problem of interpolating, and I'll talk about that later. The best emulators are things based on NR, which interpolate. Those are fantastic. But as Deirdre said, none of the emulators that we have available can include all the physics that we want, particularly when you're interpolating off of NR, because NR simulations are expensive if you make them long, so they tend to be short. So there's this hierarchy of approximations, which introduces new systematics. And even if you've done all that, we're still talking about, in some cases, weeks to do certain binary neutron star scales in MCMCs. So that's painful. Another thing that you can do is compress make these likelihood evaluations faster by doing a compressed representation of the time series, and that helps a ton. So what I'm going to talk about is something I worked on with people in this audience a while back, is trying to restructure the way that you're doing the calculation entirely from the ground up so that you don't have to do these expensive calculations, but at the same time, so it's fast, but at the same time you can still do all of the hard models, including NR. We're going to try to arrange it so we have a data product which is efficient to reuse and easy to rescale, so we don't have to run our entire analysis again if we decide, oh, maybe our spin distribution should be slightly different, or the mass distribution should be slightly different, because we're going to have the likelihood as our data product. So the basic idea is to use some fundamental properties of the universe, that it's time translation invariant, rotationally symmetric, and build that in kind of in a deep level into our algorithm, because we can put a source in the universe anywhere we want. And so taking a source that we've simulated, and we know its radiation basically in all directions from a multipolar expansion, is easy. And so doing those sorts of calculations, I'm going to call these fast parameters theta, those are trivial. And so once you have a solution to basically anything, you can put it somewhere in the universe. And so populating the universe with those signals and then marginalizing out their effect, because we're really interested in the intrinsic parameters, is easy. And then you only have to solve the dynamics once to do an analysis of that particular source anywhere in the universe at all. So this is fantastic. It's not specific to gravitational waves. And it also, as a side effect, happens to provide a natural mechanism to compress that likelihood cost. So you get both effects of the waveform cost. You only have to generate one waveform. and the likelihood, the inner products and likelihood are fast and cheap. So the algorithm that we use is we compute this marginalized likelihood, we integrate out these fast variables, then we compute an estimate based on interpolating this on some candidate trial points. We approximate it, we generate a posterior distribution, and we repeat. Now you could imagine why not do this in an MCMC? It's, well, these integrals aren't quite fast enough. And this other method that I'm proposing is also incredibly computationally efficient, as I will discuss in a second. So the production system that we use right now, this is where I'm going to talk through the data science-y issues of things, is nicely GPU optimized, works in the OSD with GPUs, it's fantastic, fully containerized, data transfer can be done with CBF, MFS, or frames. The likelihood evaluations that you're using are only about 20 seconds long, so you can make this extremely low latency if you had enough resources at the right places at the right time. The data products are either this likelihood, so you don't have sampling problems, or you can use the posterior distribution. The hardware acceleration lives here. So far, we're trying to put it in somewhere else, which is why it's only 20 seconds. And your emulators for the data science sort of things live here in your likelihood approximation and up there for the likelihood. Now, why do you care? You're probably thinking, well, this is no problem. I don't believe Deirdre. GR is easy. We have no waveform problems at all. Well, even now, I would say that for some of the events that we've already seen, there are cases where the conclusions that have been reported about events are that differ in astrophysically interesting parts of parameter space. Now, this is not a dramatic difference, but we're basically saying if you draw inferences about this particular source, which is the first source that was inferred with confidently non-zero spin, your statement that it's confidently non-zero spin is in part, the support is drawn from the fact that this black distribution does not include zero, but the purple distribution does. More ominously, if you're interested in more massive binary black holes and nature populates certain parts of parameter space, which occur frequently, then it's possible to get extremely large systematic differences between models that are simplified and include more physics. So this means that the population inference challenge that one faces is therefore complicated not only by the fact that you have to do an analysis at the end with one, let's say, perfect waveform model. You have to do it again and again and again and again because you have to account for all the possible waveform systematics that you have to try to propagate it into your answer because they will have effects. Additionally, because this is going to be so painful, I mean, if you're dealing with 1,000 effects, you don't want to have to do 1,000-dimensional times 15 MCMC every time. So it's really important, as Sean demonstrated, to reuse fiducial analyses. And that's one of the advantages of using the results from the previous code. And it's also important to be able to identify sharp features like the equation of state or fixed spin values. And also it's important to have this run fast enough so that you can use this ideally in the long run and rapid or low times so you can inform low latency analyses, although that sort of thing I haven't seen operational yet. So I could talk about the sort of stuff that you saw before, generating synthetic populations and interpreting the mass distribution, but I already showed you that. I think it's more informative because Sean already did the demonstration work to talk about a very related example demonstrating how population inference is everywhere. Let's suppose that you want to constrain the nuclear equation of state. And let's suppose that not all neutron stars have the same properties. For example, if you have equations of state with phase transitions, you can have very complicated mass-radius relationships. And some neutron stars can have quite high mass. So you might have neutron stars that live in very different parts of the equation of state space, and naive things that are proposed, not as sophisticated as Sean's more, stacking things that have the same radius, wouldn't work. But one thing that you can do with this code, without any modification or addition or complication whatsoever, the code will run right out of the box and do this, with reused, stored, archival results, is constrain both the mass ratio distribution, the spin distribution, and the nuclear equation of state, all at the same time, and you can recover what you put in. We put in things that were kind of loud because this is an injection study, just to make sure that we could recover things pretty reliably, and we can, but we're doing a more realistic population soon. I am probably not going to have enough time to get through the fun things, but Patrick isn't laughing yet. All right, so super quick. So science applications that more of you might care about, multi-messenger inference. So multi-messenger inference is basically, if you have a code that does inference, you can do multi-messenger inference. You just stick on electromagnetic likelihood. The problem, as many of you have probably encountered, is waveform models spectral models are hard, particularly if you want something that has accurate radiation transport. So what you really need to do, as been done in this paper, and you'll hear more in this session, is have some interpolated approximation. The other thing you want to do is have some astrophysical comparison. Now, the one thing you might want to do is say, I'm not going to do any astrophysical modeling, I'm going to do just phenomenology, and that's great for some cases, like if you have a robust prediction, or if you have an AGN disk, you can say, I know AGN disks are hard, but there's a couple of robust features like the IMBHs that form an AGN disk will grow linearly, so therefore I'll have a roughly a uniform distribution. But sometimes you'll have a formation model which is complicated, like, for example, binary evolution, which has to make lots of predictions, and it has to get them all right, because this is a theory which purports to explain all sorts of things. And if you're making lots and lots of predictions for lots of objects, with lots of distributions with secondary features, it's important that you include all of those features, because you may predict some of those features well, like the mass ratio distribution, and some of those poorly. And if you don't use all of that information, you're going to get a nonsensical answer. I am going to point out that therefore it's very important to have emulators for astrophysical inference. I'm going to point with Steve Taylor in the back. This is a super simple calculation that was done by Dan Wysocki, my student, where what we did is we took a one-dimensional grid of binary evolution calculations and put on a parametric spin and then evolved them forward in time, so it includes all the relevant post-Newtonian effects to conclude the not surprising conclusion that black hole spins are small. But the key issue that you should take away from this is that we're starting to enter the era where emulation of binary evolution simulations is possible and viable, important for being able to do comparisons. A much better tool, Steve is in the back, is a full parametric estimation. Suza already mentioned also that it would be really nice to use inference for detection, and these sorts of things are being done now. But I think the band is calling me off, so bye.